13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. All right, good morning. I do have two warm-ups for the day. We'll look at the warm-ups in just a moment, just after kind of the usual round of announcements, just to make sure kind of we're all on the same page. Today is Tuesday, April 21st. This is 7:45 a.m. class, and let me just do this first. So, since it is a Tuesday, yeah, just I think the key reminder is to please do the online quiz. Keep current with web work. What that means for this particular day, for Tuesday the 21st, is but it would be great to start web work 36 after tuning into this class, whether that's live or you're watching the recording after. Um, the assignment that's actually due though is web work 33. It's just good to stay on top of things. I know that there's a lot going on as the semester starts to come to a close. We have, I think, just 3 weeks, which is kind of bizarre when you think about that. Office hours are available as usual, and I did send an email actually kind of late-ish yesterday just saying that in addition to the office hours and the formats that they've been occurring, and in addition to emailing if you want a different time, that's all been there. If it helps you out as a way to show your work to me when you're stuck on a problem, you may want to screenshot something and then put it into like a Google Doc and share that doc with me, and then we could like talk about that kind of together over either video conference or a phone call. Okay, well, here are the two warm-ups. Let's start with the first of these two questions. This symbol there that's highlighted, please remember, means antiderivative of. That's the way I want you to read that. And it's too easy, it's too tempting to want to take the antiderivative of the first part and the second part separately and then to multiply the results together. That was one of the key warnings I was trying to suggest we can't do yesterday. So what will we do instead is, sorry for the second warm-up getting in the way, and this warm-up actually took up kind of essentially all this space. So I just have this equal sign and saying the original question in part one up here, it's equal to, well, we're not anti-differentiating yet, or we're not integrating yet. So because we're not doing that part of the problem yet, we're putting it off. There's still the symbol, there's still the dx at the end as well. All we're doing here is expanding or foiling. So 4x to the 6th times 10x to the 3rd is your 40x to the 9th, and so on, right? Your 4x to the 6th times 2x to the negative 7th is 8x to the negative 1st. Whenever you're multiplying things with the same base, you need to add the exponents. So that 6 plus the negative 7 is where this negative 1 comes from. So I hope that step looks okay to everyone. And then what I'm going to do right now is you may choose to skip the next step or even the next two steps, just kind of generally in your work if you'd like to, but it is still rather new, and I'd like to show the steps to make sort of a separate point anyway. It's when you are integrating or anti-differentiating, you've got several terms, like we have these 4 terms in the line above. You can split this up into 4 separate integrals. So you'll see it's a lot of work to write out, which is probably why you'll eventually want to skip writing this step. But you'll see that I've got integral dx and then a second one, integral dx for the next term, integral dx for what was the third term of 30x, and then integral and a dx for what was the fourth term. So this is a great feature about integrals or antiderivatives. It's this nice feature that we already saw with derivatives, that you can differentiate one term at a time. Does not work with a product. That's why we had expanded everything out in the first place up here, just so that we had, terms instead of factors. And then again, to now just illustrate a point and to take things one step at a time, when you're integrating or you're anti-differentiating, you have a fixed number times a function, you can bring this 40 in front. So that 40 could be written there. Same with this 8, it could be written in front. And so we'll do that. It'll look like this. So again, you may want to choose to skip this step in the future, but I'm trying to do this not only to show my work right now, not only to take it one step at a time, but to illustrate that now, in the next step, we're ready to talk about the antiderivative. So the 40 is copied because it was kind of outside. It was outside the integral, and then we have this antiderivative of x to the ninth. So when you see the symbol, always say antiderivative of, and you'll have this. So you'll end up with x to the 10th over 10 for that. Then copy the 8. So this takes up less space now because there's no more integral sign or dx. So the 8 that was there is copied over here. And the antiderivative of x to the negative first is ln of absolute value of x. The 30 is copied. And then the antiderivative of x to the first is x to the second over 2. The 6 is copied. And then the antiderivative of x to the negative ninth, when you raise the power by 1, you'll have x to the negative 8, and you'll end up dividing by negative 8 as well. And since we're done with our antidifferentiation, there's also a plus c. The key thing I want to point out about this step, and I've wrote it in blue here, is that there are no more integral signs. So what we have done is we have done each integral, or we have computed each antiderivative. We've stated what the antiderivatives of each of these four things are. Right? We anti-differentiated x to the negative ninth, and so there's no more antiderivative symbol. We could be considered done with this step, but just to illustrate another point, I'm going to just do one more step. So this stopping right here for this warm-up question would work, but I'm going to, just to illustrate a point, simplify by noting that the 40 in the numerator and the 10 in the denominator kind of cancel in part. You can cancel a 10 on top and bottom, you'll have a 4. The next term, nothing simplifies, but same deal. This 30 over 2, cancel and make that a 15. 6 over negative 8, I just put the minus sign in front, and then 6 over 8 would reduce to 3/4. So 3/4, and then just for a little algebra, so you get to think about this constant idea all the time. Instead of x to the negative 8, which you could have left it like that, I put it as an x to the positive 8th in the denominator, and there's still the plus c. So either of these last two are totally fine as final answers. But the reason I'm showing this much work, first of all, one of the reasons is just to, at least with our new stuff near the top, kind of break things down one step at a time. The other key thing I'm trying to get at is sometimes people try to treat this new process like I should always write this symbol until the second to last step. So people will do something like have the integral sign in this step and then not in that step, or something like this. But you can't, there's no, let's see, what am I, it should not be memorized where the integral sign, in what step the integral signs appear, and then in what step they no longer appear, because it's different for each problem. And how do you know? Well, again, that's why I wanted to show the work. That the thing here is people sometimes try to go through this process, go through the motions without thinking about what the symbol means. But if you keep telling yourself that the symbol means antiderivative of, then you should be okay, right? So antiderivative of x to the ninth, we are now stating what that is. It is x to the 10th over 10. That's why there's no more antiderivative of symbol. I'll just comment that you can always check your work by differentiating. We're not going to do this right here, right now, but it's a good idea just to make sure it even helps clarify even more what the symbol means. So you can take the final line of work right here is probably as simplified as possible. So I copied it down here. If you take that and you differentiate, so you do the process we did in the first half of the semester, what you'll get after factoring it ends up being what's between the integral sign and the dx. You'll end up getting that. So you've got to take this, you differentiate, and if you factor, I know the factoring will look a little strange, but you'll end up with that. So I hope that works for warm-up question 1. I will just pause for a second and see if we've got any questions coming through. There is a second warm-up question, and it's if h of x equals e to the power x to the 5 plus 6 to the x, find the derivative. So we're not anti-differentiating this, we're finding the derivative because it naturally flows into what we'll talk about today. I'll put that question at the top of the next slide. And then let's, the key thing I want to point out here is that this is going to require the chain rule. And if you feel comfortable without showing all the work related to the chain rule, that's totally fine. But what I want to do is, because it's going to relate to what we do next, I'm actually going to show all the pieces and kind of all the level of detail that we first did this kind of thing. So if your external function, and I'll even use as the input variable for the external function a u. When we had first learned the chain rule, there was a u there instead of an x. You may be very comfortable using an x there, but there's a good reason to use a u today. If the exterior function is e to the u, so that accounts for this e to the, and then something part. And then the interior function, I of x, is x to the fifth plus 6 to the x. Then just piecing together all the pieces for the chain rule first, we'll just compute some derivatives. First of all, e prime, capital E prime. So if you have little e to the u power, the derivative is e to the u again. So e to the u is this strange function that once you take the derivative, you just coincidentally get back the same thing. By the way, it will come up a little bit later then that when you need the antiderivative of e to the u, it'll be e to the u. So I hope I pointed to the correct e to the u as I did that. If the derivative of this e to the u is this bottom e to the u, then the antiderivative of this bottom e to the u is this top e to the u. That'll come up in just a moment. We also need to compute the derivative of I. So the x to the fifth one, its derivative uses the power rule, 5x to the fourth. The next term is 6 to the x, though. No power rule there. You've got to use the exponential rule, and you get 6 to the x times ln of 6. In the chain rule, we'll need to piece things together, right? So we are, first of all, just as a reminder, using the chain rule because the function we were asked to differentiate is a composition. And to find the derivative, here's what the chain rule formula says you do, right? E prime of I of x times I prime of x. So we'll build the pieces. So e prime of I of x, take this function, compose it with I of x, and you have e to the x to the fifth plus 6 to the x. But then there's a times. That times sign is just copying that time symbol there. The times sign is actually optional here. The parentheses are not optional though. And then you need I prime of x. So I made a copy of that right here, right? Parentheses are not optional because you've got two terms and order of operations here matters. So yeah, the parentheses here are necessary. Okay, so that computes the derivative. We were asked to find h prime of x, and after showing a little extra work, here it is. But the purpose of this question, so it's not just about the warm-up, it's about trying to lead to the next thing. So I'm going to say the following. We just computed the derivative of this up here, and the derivative, so here it is again, it says derivative of that, and this one's a little different in red, but not by much. There's this plus c, and if you differentiate that second term, which is a constant, you're going to get a 0 anyway, so the result of the derivative should be the exact same as what you had right up there. The whole point right now is like yesterday and the day before, yesterday and last Thursday, I'm using this color coding to show what happens if you swap, right? So if you put this thingy over there and this over there, in the process of swapping like this, you do need to switch the symbol being used as well. So instead of derivative notation, we have antiderivative notation right there. Okay, this is going to be key for us in just a moment. So the process we did was going forwards. You know, if derivative is going forwards, you start with e to the power x to the 5 plus 6 to the x, and once you're done differentiating, you get this. Now we're going to take this statement right here and think about the process, believe it or not, of going backwards from here. So what if you start with integral of, or antiderivative of, e to the x to the fifth plus 6 to the x times quantity 5x to the fourth plus 6 to the x ln of 6. Then how would we end up getting this text in red if we weren't given this first? So the first time around, what we're going to do is we're going to borrow some ideas from this slide and start exploring how we might have come up with this without any of the information that we're taking from this slide. So we're going to discuss undoing the chain rule. That's today's new integral rule, or today's new anti-differentiation rule. So suppose we were given this problem. We're just given it out of the blue. Antiderivative of e to the x to the fifth plus 6 to the x times quantity x 5x to the fourth plus 6 to the x ln of 6 dx. Please write that dx. That's going to be really important in what we do. So we were given this kind of out of the blue. Now this was copied from the bottom of the previous slide, just so you know. But let's just say we were given this, no context. We weren't working on a warm-up or something like that. Okay, like a week from now, if you're given this, what should you do with this problem? Just to make sure and state it and connect it back to the warm-up we did, this question is asking the derivative of what? Fill in the blank here is e to the x to the fifth plus 6 to the x times quantity 5x to the fourth plus 6 to the x ln of 6. That's what the question is getting at, but how are we going to do this? The point is, if the function that we're looking for in this spot, now we know just from the warm-up, but let's say we didn't. If the function that we were looking for was differentiated using the chain rule, we need to figure out what the interior function was. That interior function we've called capital I of x, but for convenience we're going to try to call it lowercase u. How do you get what the interior function was without doing a warm-up like we just did? You're not going to maybe like this answer in a math class, but you're going to guess. We're going to talk in just a moment about how you guess well, like how there's a bit of an art form to this process. But for right now, we're going to just have u equals x to the fifth plus 6 to the x. For right now, instead of guessing in the true sense of guessing, we're going to borrow this from the warm-up that we just did. So on the previous slide, we had said u, the interior function, was x to the fifth plus 6 to the x. So again, I get that this was copied or borrowed from the warm-up from the previous slide, but let's say we guessed this and this was the correct guess to make. What should we do with this? What I'd like to do is compute the derivative, and I'm not going to write u prime. I'm going to use that other notation today. It's going to be much more helpful. So instead of writing u prime, I'm going to write du over dx. So I encourage you to write these steps with me. Whether you're in the habit of note taking for this class or not, this I think is going to be very, very key. So you might not write all this text, I get that, but please write down u equals x to the fifth plus 6 to the x. One line down, write down du over dx equals 5x to the fourth plus 6 to the x ln of 6. I know it's a lot to... This format doesn't make it easy to stay as active, I get it, but like at least writing this down, just the times that I'm begging, pleading for that, I think it'll help. Now the next step we're going to do is going to sound a little strange, but we're going to multiply both sides by dx. So this is where the book and WebWorks notation of putting this kind of dx kind of all over the place, like in the numerator sometimes, is helpful. I want you to think of, so we're multiplying both sides by dx. I want you to think of dx, even though it's two separate letters technically, I just want you to think of the two letters glued together. It's like a variable that's two letters long. That's all, right? So multiply both sides by dx, and then if you multiply on the left side, by multiplying by a dx, the dx you introduce in the numerator is going to cancel with the dx in the denominator. On the right side, we'll just wrap what we had in parentheses and then just have this dx out there. So this is what multiplying both sides by dx would look like. So yeah, be sure to have that step. Then the next thing we're going to do from here is we're going to solve for dx. So treat this like a variable. Treat this like its own variable. Pretend it's a z or something if you want for a moment. And we're going to solve for dx. So notice that on the right side we've got stuff in parentheses times dx. So to undo the multiplication we need to divide on both sides. So we're going to divide both sides by what's in parentheses. And so we'll have on the left side the du that was there before in the numerator. That du is there. And then we also, what we just divided by on both sides, we'll have 5x to the fourth plus 6 to the x ln of 6. That equals dx. So here it is. Dx is by itself isolated on one side of the equation. We have solved for dx. Okay. Again, a lot of this is built on the backs of having made a proper guess for what u is, and that's probably the main question right now. But before that question, I need to kind of just finish off this process and then we'll see. So let's say we were given this problem, and the kind of only key information we were truly borrowing then from the previous slide was this interior function that u was x to the fifth plus 6 to the x. Based on this one line right there, we did these other lines of work, and this process will always be the same. You'll multiply both sides by dx and then solve for dx. That will always be the same. What I want to do is take the problem at the top. So I copy this down here. I'm going to give you a moment to copy down the problem as well, because this is gonna take up quite a bit of work. So, and that's how these usually go. So let's get used to it now. So if I could please have you write that down and then write down an equal sign. Now, after the equal sign, I would like to write down what's all here again. However, I would like to replace this dx that appears right there. That's the only replacement we're going to make. Later on, when you feel more comfortable, you might do a couple replacements at the same time. So first, look, there's a first time around. If the problem, if one step to the next, what we have changes by too much, it'll be hard to look at and keep track of. So it's going to take extra work, extra steps right now, but just one thing at a time right now. So let's just replace the dx that appears right there. So replacing the dx, and how do we do it? Well, that's why we solve for dx. The dx gets replaced with this fraction. It's going to take a little extra writing, but let's write that out. So making that replacement, so I highlighted in this step in red where we're borrowing from. So what's the same is this integral sign, e to the blah, that stuff in parentheses, all that's the same as before. The only change is this dx that's right there. I'm kind of underlining it a little differently. Got replaced with this fraction. And that's borrowed from what's in red currently, right? That if you see a dx, you could always replace it with a du over 5x to the fourth plus 6 to the x ln of 6. I'll get rid of the underlining so that we can okay, the thing that I want to point out about this step is you'll see this 5x to the fourth plus 6 to the x ln of 6 once in the numerator and then once in the denominator. So those cancel out. Not that, okay, so you could draw in the cancellation or not. Sometimes drawing in cancellation lines makes it more confusing to look at later. But if those cancel out, then all you're left with is this integral sign e to the that power and then just the du because everything else canceled. Now this thing is that power, x to the fifth plus 6 to the x. We have it right up there. That could get replaced with u as well. So you'll have this, right? So this whole problem here, after the cancellation occurred, and then you replace, and I've highlighted this in red right up here right now. If you replace the x to the fifth plus 6 to the x you see with a u, you end up with integral e to the u du. So take a look at where we were just a moment ago. We had this huge problem. The only variable was x. But now, after making some replacements, we have this new problem. It's way smaller. It's integral e to the u du. Now there's no more x's. The only variable is u. And now we need to answer the question of what's the antiderivative of e to the u. So this is a problem we had looked at actually last Thursday. You heard a repeat of this idea of antiderivative of e to the u yesterday, and you heard it again today that since e to the u is its own derivative, e to the u is its own antiderivative. So for an antiderivative, we're now reporting what the antiderivative is. We computed the antiderivative, but just is that coincidental function where it's its own. This function is its own antiderivative. So we're stating here that the answer without an integral sign after the equal sign is e to the u plus c. And then one last thing we do in this question is we replace the u, because the original question that's here or up here never had a u in it. We just introduced the u to try to ease how we have to think about this, but now we're just going to replace the u, and that's where having this u equals x to the fifth plus x to the 6 to the x is helpful. So the u that's right there, let me maybe just circle it, the u that's there got replaced with this right there. And we're done with the problem. So I'm going to pause, and there's usually lots of questions. So let's wait and see what comes up questions wise. Yeah, let's find out how we're doing. Yeah, do we always end up with a du? Yeah, so that's a good question, and you actually always do. So let me just try to point out the reason why. So in a different problem, the choice of what u is right here might be something different, and I'll be able to erase everything out. So let me just kind of scratch that out. Excuse me, I got to cough just for a minute. So let me mute the mic. Okay. Sorry about that. So yeah. So what you have for you is going to be different in a different problem. But like whatever it is, then in this next spot you end up computing a derivative, and then that same thing you'll see kind of right there, right? And the point is, the general process here is always going to be the same. You've got u equals something, then you have du over dx equals whatever the derivative is here, and then you always multiply both sides by dx next, so that you have dx in the numerator instead of the denominator. And then when you take what you have here and you divide by that on both sides, that ends up here. You always end up having a dx equals the fraction du over something. So the dx always gets replaced with du over something, and the du always ends up in the numerator. So I hope that addresses that. Do we always end up with a du? Yeah, this is the argument that no matter what you have for u here, in this, if you apply this process, this new kind of procedure isn't always the thing to do. Like yesterday, we did some integrals without introducing this u and du business. But if you do it this way, you will always have a du. So other questions, or did I answer that question properly? You could ask us an extra question. Or do they always cancel out, or is it in certain problems? Yeah, that's a good question too. Like what happened here was we had this thingy and this thingy cancel, and that. So do they always cancel? I'll say they don't cancel if you pick u improperly. So that's the hard part of this process, is that if you pick u properly, everything cancels the way it needs to. If you pick u incorrectly, you might get stuck and things don't cancel. So when things don't cancel the way that you were hoping they do, maybe what you need to do is go back and pick a different u, or maybe you need to use a process that's not this u thing, but go back to like what we did yesterday. So our goal is to try to make sure that that cancellation always happens. Right? So do they always cancel? If you select u correctly, yes. So then the next question becomes, how do you select u, right? And that's what we're going to start to address in our next. You have to kind of see the whole process through just before talking about what cancels. Or like, do they always cancel, and so on. These are good questions. Anybody else? I mean, or, anybody have another question? Yeah, so our goal is to try to get cancellations to happen. Because you want to go from a problem that has all x's to a problem like over here that has all u's. That is part of the goal. Should we start talking then about in another example problem? So without borrowing from a warm-up, how do we properly guess what u is? I think that's probably where the next questions lie. So I'll advance to the next. If it was e, wouldn't we already know u? E as an e to the x. It really just depends on the problem. So often when you have an e to the something, usually that thing up there is u, but there's no complete guarantee. You got to look at kind of the rest of the problem, and there's a lot. I mean, yeah. So often when you have e to a power, the power ends up being u, but it can't always be that. So it depends on everything else, because you're always trying to get something to cancel. So it depends on kind of a number of pieces that need to fit together. So keep asking questions, because there's always sort of this lag of time between when I say things and then when I finally get a response back. But what I'd like to do is at least start addressing how we would guess what u is. And first of all, the guess for what u needs to be shouldn't be wild. It should be somehow built into the problem you're looking at. So it is dependent on the problem, but in this problem, you'll see that the u we picked was hiding right there. And that feature you'll see, and in fact, because of that, here's a new question. This was not connected to a warm-up we did, and I will say the following, that what I want you to do how do you pick u? It's usually, there's sometimes some very rare exception, but usually it's part of what you see within the problem. So you look at this integral problem, and I want you to the approach I think to take is to zoom in as much as possible, right? So like you look at the problem, and if you're like super zoomed in, maybe just, oh, I zoomed in too far. So maybe you zoom in. I want to zoom in more, but I don't think the computer's going to let me. You zoom in and you see this X right there. So maybe that's you. Or if you zoom out just a little bit from there, then you'll see an X squared. Maybe that should be you. And let me erase that. If you zoom out a little further, in view, maybe you'll see a 1 minus X squared. So maybe that's you, right? If you zoom out further, maybe you'll see this root 1 minus X squared. Maybe that's you. Or if we go to the numerator and zoom in a little bit more again, maybe it's X, although we already had boxed X and mentioned that option. But if we zoom out just a little bit from there, then we'd see the 3X. So sorry, I wanted to zoom in even more, but I don't think the thing will let me zoom in quite as much as I want to. So sorry for that little, I hope you're not dizzy after that little process. But you look at the problem, and I like to think of it like I zoom in a lot so I can barely see the rest of the problem. And anything that I see that's an expression seems to be an option. So having done that silly experiment, here are some options. Let me kind of actually now, I spoke through some of them, but let me write down what I'm trying to run through. So like somewhere in the problem, I see X. That's by zooming in so much. Like my eye is so close to the board that all I see is X. If I just step back just a little bit more, I was staring at the numerators clearly, right? Then I might see a 3X. If I don't step back, but I just maybe rotate my head a little and just a little bit down and to the right, I notice an X squared instead. But if I zoom out a little more, I'll see a 1 minus X squared. And if I zoom out just slightly more, I'll see square root of 1 minus X squared. And this one maybe requires a little more creativity, but I also see within the problem a 1 over square root of 1 minus X squared. You kind of have to push that 3X off to the side, which is a legal algebra move, So it's what I'm trying to get at is when you do this process, if this is the right process to apply, it's usually one of these kinds of things, something you see within the problem that's going to be you. I will point out though, if by zooming in too much, specifically whenever you pick u equals x, it's never gonna work out for you. In fact, all you do when you end up picking u equals x is you end up rewriting the original question with all of the x's as u's anyway. So that I would not pick that choice. So it's the one choice I want to just chuck out from the beginning in terms of options, but then something else from the list. So it turns out in this problem that u equals 1 minus x squared is going to work. How do I know? Again, this is where, because this is only going to be our second problem we're demonstrating, I'd like to go through it, and I'd like you to see the thing that cancels, and then we'll talk about it a little more. So I just want to, sorry if this is a little like, I want to give you more insight into how did I pick this one out of all of these other choices? How did I know to pick that one? You'll see in just a moment. So at the top of the next slide, I've got the problem copied down, and I have this circled selection for you. Okay, so there's the question again. Evaluate is often the word used. Evaluate antiderivative of 3x over root 1 minus x squared dx. So there's that selection of u from the previous slide. I wanted to have the previous slide show you all these different options for u, but so that it wasn't confusing on a new slide, I'm only showing you the good option for u. Okay, so what we did in the previous question after selecting u was we computed a derivative, so we'll do that here. Du over dx is the notation we'll use, so no u prime. U prime is technically correct, but it's just not going to be helpful in what we're doing right now. So du over dx equals, the 1 differentiates to a 0, right? Constant differentiates to 0. After copying the minus sign, x squared using the power rule differentiates to 2x. We need to solve for dx, right? Let's solve for dx. The first step in the process is always to multiply by dx on both sides, because always when you do this, you have dx in the denominator, right? We always had a du over dx. So let's multiply by dx on both sides from the previous step up there. And then to solve for dx, divide both sides by negative 2x. So you'll have I swapped the two sides, but you have dx what was on the right side before it, I wrote on the left side, equals du over negative 2x. Cool. So we've got the pieces that we need. Now let's go back to the original question. And our goal then is to take the equations we have here in the bullet points and make replacements that are valid. So the goal here is there's no need to make up anything. So I copy down the problem. We'll make replacements that are valid in that, like for instance, this dx right there, we are allowed to, it's valid to replace dx with the fraction du over negative 2x. So we'll make that. That's the only replacement made from here to there. The thing to point out then is that you'll see the x in the numerator here and the x in the denominator there of this fraction, those cancel. That's the cancellation we needed. You might say, okay, so there, right? So here it is before cancellation. Here's the same problem after the x is canceled. And you might say, hey, what about that negative 2 though? I'm not really all that worried about the negative 2. Okay, because that's a number, right? Or it's technically a negative 1/2. But when you just have a number times a function, in your integral, that number can come in front of the integral anyway. So yeah, things didn't fully cancel, but the key thing that needed to cancel was the variable, and that we got rid of. There's one other replacement we can make though. You see how right now there's this mix of, there's a du, there's a u there, there's an x there. Oh, two variables in the same problem? No thank you. We can actually replace 1 minus x squared, because we have here that that's what u is. So we'll make that replacement as well. So going from this version of the problem to that version of the problem, the only replacement, just you might get comfortable doing multiple things all at once later, but the only replacement I made here is replacing the 1 minus x squared with a u. Here, getting you at least slightly used to talking about that kind of strange notation of having the dx in the numerator or the du in the numerator now helps sort out what we'll do in the next step. The next step is not it's not calculus so much, it's more, I just want to rearrange things because this just looks a little funky to me. Maybe you'll be used to this later, but here's how I wanted to organize the question. So I've got the integral sign, and then the 3 over negative 2, I wrote it as a negative 3 over 2. The minus sign can be on the top or the bottom, just one place or the other. So I wrote the number first, and then this root u is in the denominator, so that's why it's a 1 over a root u. So it was in the denominator before, should remain in the denominator. And then instead of having this du kind of in this funky spot in the numerator of a fraction, I just wrote it off to the side. So it's just, all this step was just kind of juggling things around, but if it was in the numerator before, whatever things were in the numerator before are still in the numerator, things that used to be in the denominator are still in the denominator. Okay, and then just to like kind of illustrate a point, and again, if you skip this next step, at least in this fashion, I get it, but there's a number, that's a plain number, negative 3/2, it can come in front of the integral sign. And then in addition, I'm going to rewrite 1 over root u. So that's 2 steps in one, but the negative 3/2 is written in front of the integral sign. And then u to the negative 1/2 power. So the negative exponent to account for having been in the denominator, the 1/2 as an exponent to account for the radical du. But what the whole point is, already up to back here, and then this one, and the last 3 versions of the problem we wrote down only have one variable all the way throughout. It's not a mix of x's and u's, it's just u's. So now let's take a look at this problem. Integral u to the negative 1/2, and say, you know what? It's variable raised to a fixed exponent. We have to undo the power rule, and we have a formula for that. So I copy down the negative 3/2, and then we need to now finally anti-differentiate u to the negative 1/2. So you've got to raise the exponent by 1. And when you do negative 1/2 plus 1, you have a 1/2. So u to the 1/2, and then you have to divide by the new exponent. Notice this is the step. This is the very step in which we are computing an antiderivative. That's why we used to have an integral sign or antiderivative sign, and now we don't. We instead have a plus c. And then we're not quite done. The original question right up here didn't have any u's in it, but our answer currently does. We've done our antiderivative work, but this is now the step in which we take the u that's right there and we go back and replace the u with 1 minus x squared. So we're done with this question, but let's pause again and see how we're doing. Questions that come up, I guess while you're thinking of a question, I'll just say, if we picked a different u, things probably would not have canceled. Here, even, not everything canceled, because we canceled the x's here and here, and we're left with this -2, but look, that -2, ended up as the -2 that was in the denominator inside the integral sign ended up as a -2 in the denominator outside the integral sign. Would the 2 and the 1/2, so this 1/2 in the denominator, yeah, and this 2 also in the denominator, yeah, you could cancel those out and just have a 1. This is one of these things where I was like, yeah, so if you want, you could, these two things cancel each other out, but because it's a 2 in the denominator and a 1/2 in the denominator, and they're being multiplied. But I just, wanted to, so yeah, if you want to, you could write a final answer as a, whoops, I did not mean to zoom in, as a -3 times quantity 1 minus x squared to the 1/2 plus c. And for that matter, so that's, the point is, this one's a good final answer, this one's fine as well, and if you really wanted, you could even take care of this 1/2 exponent and write this as -3 and then root 1 minus x squared plus c as well. So you got, like, any one of these three here would be okay as final answers to me. So kind of a lot of replacements, but one of the key replacements is replacing this dx with this du over -2x, right? So that's this replacement that we did there. That replacement isn't possible if you don't write dx. This is the problem I've seen a lot, and that's why you heard me. This comes from the experience of having, I think this is the 6th time I'm teaching 175 now, but at the first couple times I taught the class, I didn't make much of an emphasis of, hey, be sure to write that dx, make it a habit. And then it was only in office hours once I realized where people were getting stuck. They never made the replacement of dx turning into that fraction, but how could you if you don't write the dx? So if you don't write the dx, how are you going to replace dx? So that's why it's, I think, key to write that down. Just stepping back for a moment before we look at another example, I want to say that I would not write these steps down right now. Okay, we're going to write down a better version of this on the next slide with more detail. But while I had barely enough space to write something, I wanted to write down some key ideas and point to where these ideas appeared in the problem we just did. So first, you've got to pick u, right? How do you do that? I'm leaving that for the next slide. Then once you've picked u, you've got to compute d over dx, compute a derivative, and solve for dx, and that process took up to here for us. Then you end up replacing the u and the dx. You could do these in any order or even combine them. So we replaced the dx here with this fraction. We replaced u, or sort of backward. We replaced 1 minus x squared, technically, and put a u in place for that. But I didn't quite know how to phrase that here because the u that you have is different in every problem. So I hope you get what I mean here by replace u. Then you do so then your new problem after the cancellations occur should only have u's in it. And then we kept simplifying that integral. And then you need to do that integral. So this language sometimes gets people. So on the next slide, I clarify even more. But do the integral, meaning find the antiderivative. And then once you've done that, so here we are having done the integral, there's no more integral sign, then you need to replace u in the other way. So that's what I mean here by reverse replace. I know the language is a little awkward, but earlier we had replaced a 1 minus x squared with a u, and now there's a u, we replace the u with a 1 minus x squared. So at least kind of stepping back and looking to this problem as kind of an example of the overall process, here's what occurs. I would like to spell this out in a little more detail on the next slide. This is the thing that I think should perhaps be written down actually then as a process. So we're going to undo the chain rule. This thing is called substitution. So within the function you need to integrate, you pick u. How do you pick u? here's where I'm going to now provide, this doesn't always work, but like 90% of the time, what's in parentheses is the right idea. If you see the derivative of what you're going to say is u elsewhere in the problem, so I'm going to say, I think u should be this. And then you look somewhere else in the problem and you see the derivative of this. Right? You say u is going to be blah, and the derivative of blah is elsewhere in the problem. That's probably a good choice for you. That's going to usually lead to the cancellation. Not always, but that's the right idea. So you pick u, and in parentheses is the hint of kind of how. You compute the derivative of u, so compute du over dx, solve for dx. Sorry, I realized I was getting excited, so I need to calm down so I don't go too fast here. Compute du over dx, step 2. Step 3, solve for dx. And then you make some replacements. So you replace something with a u, and then you replace the dx. And then you're hoping the cancellations all work out. So if all the x's go away, the substitution was successful. What I'm trying to get at here is maybe you pick something for u, and you don't know at the moment, but maybe the thing you pick for u doesn't really work. So if you try to do all these cancellations and you can't seem to cancel what you were hoping was canceling, and you have this new problem that has both x's and u's, that's a problem, right? Like, you went from a problem that only had x's to a problem with two different variables in it. Not a good idea. So if all the x's don't go away, like you're not able to cancel what you hoped would cancel, go back, pick a different u, or maybe this method isn't the method to use. Maybe you need to go back to like what we did yesterday. Anyway, you're hoping that all of the x's go away before moving on. I've seen people not bothered, let's say, by having both u's and x's and try to do the next steps. It doesn't work out. Like, the whole point of this process is to take one kind of busier looking problem and make it less busy, but it should have just all the new variable u and none of the old variable x. So you take this new integral that only has u's in it, and you do this integral. What I'm trying to say by do the integral that has u's is find the antiderivative. Right? Integral, that symbol should still be there. It means find the antiderivative. And when you are finding that antiderivative, don't forget the plus c, just as a reminder that that plus c belongs in this step. And then once you have found that antiderivative, the original question didn't have u's in it, but your antiderivative does. So as a final step, all you got to do is now replace the u. So that's the overall process. We'll state it a little differently tomorrow. Just to help clarify different aspects of it. But I will say that you need to do the integral, that is, find the antiderivative, do step 6 before the final replacement of u in step 7. In other words, do step 6 and then do step 7. I have seen people try to swap to try to do step 7 and then do step 6. It's kind of missing the point of what's going on with the substitution. The whole point is, if you replace u first, you'll have u's and x's, and like you'll have a two variable situation again in trying to find the antiderivative. You don't want to do that. So don't try to swap the order of the last two steps. Don't try to combine the last two steps and do them at the same time. It's one thing at a time here, right? So you've got this problem that has u's in it. Find the antiderivative. Don't forget a plus c. Once you've done that, only once you've done that, then after do step 7. Step 7's nice. You just make a replacement, but still don't combine it with step 6. I see people try to do that all the time. So let's finish off with one more here. So I've got antiderivative of the fraction 4x to the second over x to the third plus 6 dx. So even in writing down the question now, I hope you're seeing why I was making such a fuss over needing to write the dx, so please do that. Here are some ideas for you. I'll just all at once. Not that you need to write down this whole list, okay? I just want you to kind of enter my brain for a moment of like, where did I, like, I hope each one of these selections of what u is, you see where I was going, right? Like, I hope what you're seeing is this idea that somewhere within the problem, if I zoom in enough, like the problem is written like on a huge poster, and I like walk up to it so I don't see much of the rest of the problem, you can see, I hope, within the problem where the many possibilities of u seem to have come from. And then let me now, having provided a list, and you could, here's the thing, you could just kind of go through the list one at a time and just pick and then try. And that's not a bad idea at first, but I will point out that picking u equals x cubed looks promising. The reason it looks promising is the derivative of x cubed is 3x squared, and at least we have a 4x squared. And I get the 4 in front of the x squared is not the same as a 3 in front of an x squared, but these constants are going to work themselves out. They're going to pull in front of the integral anyway. So even though the u equals x cubed looks promising, actually what tends to be a little more promising is u equals x cubed plus 6. The reason is when you differentiate this constant 6, you're just going to get a 0 for the derivative of 6 anyway. So typically, generally speaking, when you pick u and you see an option that seems like it's going to work and give you the cancellations you need, typically if there's a plus and a plain number like there is in this problem, you typically want to take that number with as part of what u is. So let's try that. Let's try u is equal to x cubed plus 6. Again, picking u is a bit of an art. Let's go with u is equal to x to the third plus 6. Du over dx, the derivative is 3x to the second plus 0. I just didn't write the plus 0. We need to solve for dx. So as a first step, multiply both sides by dx. So you'll end up with du equals 3x squared times dx. And then to solve for dx, you've got to divide both sides by 3x squared. So you have du over 3x squared equals dx. Okay, these are all the pieces that we need to have computed so that we can now go back to the original question up at the top. I've rewritten the question. But now let's make some replacements. So this time around, I'm going to make 2 replacements. So I'm going to reveal that next step, see if you're okay with it. So I still have the integral sign, right? So making substitutions is an algebra-like idea. So that's not finding an antiderivative yet. That's why there's still the antiderivative of symbol. But there's the 4x squared. Instead of writing x cubed plus 6, I replaced that with a u. That's why there's a u down here now. The dx got replaced with the fraction. Dx got replaced with the fraction du over 3x to the second. Okay, hopefully things cancel, or enough things cancel. So the 4 and the 3 don't cancel, but at least the x squared and the x squared cancel. X squared in the numerator cancels with x squared in the denominator. Instead of 4 in the numerator and 3 in the denominator of different fractions, I just put the 4 in the numerator and 3 in the denominator of the same fraction. There's still a u, but that u was in the denominator before. Don't magically make the u just move up to the numerator. It was in the denominator, it remains in the denominator. That's why this says 1 over u and not just a u. And then finally the du that was in the numerator, I just wrote that off to the side. So you can bring the 4/3 in front or just copy the 4/3. It's at this point we now actually compute an antiderivative, so there's no more integral sign. So when we antidifferentiate 1 over u, we get ln of absolute value of u plus c. Right? So sometimes the mistake people make, instead of going from here to here, sometimes people at this stage want to replace the u. Don't at this stage look at this u that I'm pointing at right now and replace it with x cubed plus 6. That would create a problem where you have not then done the antiderivative yet, and the problem would both have u's and x's in it. It would be a mess. Like we did all this hard work to get to the stage where this new problem only has one variable throughout. It's u's throughout, just like the original problem had x's throughout. But if you look, this new problem is way nicer than the old problem. So let's take the new problem, which is just in one variable, and just the variable u, and compute an antiderivative first. Having computed an antiderivative, we were like in u land for a moment. Now what we can do, now that we've computed the antiderivative, we can now make the replacement of u is x to the third plus 6. We'll have 4/3 ln of absolute value of x to the third plus 6, close absolute value plus c. This integral has been computed. An antiderivative with a plus c has been stated. Right? So the point is we had an integral, we computed an antiderivative, there's a plus c there. After that step, then we replace u with x to the third plus 6. I figured we wouldn't have time for this next one, but I do have the work written out. So I'll just give you a chance. We have another problem tomorrow that looks very similar to it. I'll just end with so if you want to look through the problem I just kind of advanced through quickly as another example, fine. But I'll just again point out today there's an online quiz, so please complete that. And I would highly encourage you to look at WebWork 36 today. Start that. I'm not saying you have to finish it. If you're starting WebWork 33, that's the one that's due today. You're going to feel a bit of frustration with what's going on in tuning into class and in grades and in completing things and so on. All right, so again, main thing, please quiz today, and then we'll see you for class tomorrow.